Welcome to Chapter 7. In Chapter 7, we discuss sampling and sampling distributions. We look at information that we can get from samples and what we do with that information. Please make sure that you've mastered Chapter 6, especially the use of the normal distribution and the use of the standard normal table. To refresh your memory, a population is a collection of all the elements of interest, and a sample is a subset of the population. We draw a sample from the population, and we derive information from that sample. Why do we draw samples? The reason is simple. We want to answer a question about a population. But because the sample contains only a portion of the population, the information we obtain will provide us only estimates of the population's values. So we won't get the full picture. These will just be estimates or snapshots. But the nice thing is that, and please look at the fourth box, with proper sampling methods, the sampling results can provide good estimates of the population's characteristics. So it's important to have proper sampling methods. There are two further things to think about. We have to think about what is the population we are drawing the sample from. And there are two types of populations. One is finite, one is infinite. What's an example of a finite population? Please take a few seconds to think about it. Here are some examples of finite populations. An organization's membership, the numbers of the credit card accounts, the numbers for the inventory. One simple example is our class, for instance. There are 60 members of the statistics class, hence the population is of size 60. And what we would then do is draw a smaller sample from that population. Some nomenclature here. Capital letter N is the size of the population, which in this case is 60. A small letter n is the size of the sample, for example 5 or 8 or 10. There are then two ways to draw a sample from the population of 60. One is draw sampling with replacement, and the other is sampling without replacement. And if the population is large enough, we may have to use random number generators in order to get the members of the sample. That, for instance, is easily done with Excel. So here's an example. St. Andrews College has 900 applications for admission, and the applications were numbered from 1 to 900. As you can see, the population, capital N, is 900. The director would like to select a simple random sample of 30, which means small n equals 30. What the director could then do is assign a random number to each of the 900 and then make a simple drawing. But sometimes it is not possible to obtain a list of all elements in the population. Hence, we cannot use the random number selection procedure. This usually happens when the population is infinite. But be careful, this does not necessarily mean that the number is truly infinite. So here are some examples where we may need to assume that the population is infinite. The parts being manufactured on a production line, transactions occurring at the bank, telephone calls arriving at a technical help desk. What's happening is that the members of the population are always arriving, and we have no way of knowing what the upper limit is. In that case, this is how we should create a random sample. We should basically just make sure that each element in the sample is really from the population of interest, and we have to make sure that each element in the sample is selected independently. In this course, we won't be dealing much with the mechanics of actually administering samples, but we'll be focusing on the analysis of information obtained from the samples. Let us now focus on point estimation. In point estimation, what do? We use the data from the sample. We then compute a sample statistic, and we then use that sample statistic to enable us to estimate the value of the population parameter. For instance, we refer to the sample mean, x bar, as the point estimator of the population mean, mu. That is to say, we draw a sample, we get the sample mean, and we make that sample mean an estimate of the population mean. Similarly, the sample standard deviation small s is the point estimator of the population standard deviation sigma, and p bar is the point estimator of the population proportion p. Here's a concrete example. As you recall, St. Andrews College received 900 applications. The director would like to announce the average SAT score of the 900 applicants, as well as the proportion of applicants that want to live on campus. But because the director is pressed for time, he or she is not able to get the actual average SAT score of all 900, or the actual proportion of the 900 that want to live on campus. So this is what the director can do. The director uses computer-generated random numbers to draw a sample of 30 applicants. Let's recall. That's the sample mean, or x bar, is the point estimator of mu, the population mean. So from the sample of 30, he found that the average SAT score was 1097. He also found that the standard deviation of the sample of 30 was 75.2. And he also found that 68% of the 30 randomly drawn applications wanted to live on campus. So what we then say is that these three numbers are our point estimators of mu. But be careful, different random numbers would have identified a different sample, and therefore the sample mean, sample standard deviation, and sample proportion would have been different. So if by totally randomly drawing a sample he had gotten a different set of 30 applicants, these numbers would probably be different. It would have been something like 1100 or 1088 for the sample mean. Let's now look at the next day. After all the data have actually been entered, these turn out to be the population parameters. So the 900 applications have a mean SAT score of 1090, a standard deviation of 80, and a proportion of 72% that want to live on campus. Let's compare the point estimators with the actual population parameters. As you can see, our estimates are not very different from the population parameters. The sample mean is 1097, whereas the population mean is 1090. The sample standard deviation is 75.2, and the population standard deviation is 80. The sample proportion, wanting campus housing, is 68%, whereas the population proportion is 72%. Here is some practical advice. Whenever a sample is used, we should make sure that the targeted population and the sampled population are in close agreement. For instance, before a presidential election, if you want to make a sample of people's preferences for voting, since the election is national, you should make sure that your sample draws from all regions of the United States. It should also draw from all ages. It should also draw from all ethnicities, income levels, genders, and so on. For instance, suppose you sample 30 individuals about their presidential preferences, and all 30 individuals come from just one neighborhood, or are all one gender, or are pretty much the same age. Then, your sample will not provide you very good information. Diagrammatically, this is how it's done. You start with the circle on the left. We have a question. What is the mean of the population? What do we then do? We draw a random sample with small n number of elements. We take the sample mean of that sample, and the sample mean that we've calculated, we then use as an estimate for the population mean, mu. The same procedure would hold for the standard deviation and the proportion. What is the nice thing about this? If you recall, the sample mean will be different depending on the sample. If I draw a sample of 30, I'll get 1090. If I get another sample of 30, I may get another sample mean of 1088, or another sample mean of 1091, and so on. Hence, the sample mean is itself a random variable. And remember, a random variable will have a probability distribution. So the probability distribution of the sample mean is just called the sampling distribution of x bar. Also remember that a random variable will have an expected value. Think of it as the average of all the possible values if you write them all down and if you keep trying that random variable. Similarly, if we keep drawing a random sample of 30 and keep writing down the sample mean, pretty soon we'll have a sheet of paper with many, many numbers. If we then take the average of those numbers, we would expect the value to be the population mean. And this is the result in this box, that the expected value of x bar is the population mean. This is a nice property to have. We say that the point estimator is unbiased if its expected value is equal to the population parameter. Let us now look at the standard deviation. Here is some notation. Sigma x bar is the standard deviation of x bar. Sigma, without any subscript, is the standard deviation of the population. And as we've discussed, small n is the sample size, big N is the sample size. So as we've said, x bar itself, the sample mean, is a random variable. Random because each sample will produce a different sample mean. Now, as we remember from chapter 6, a random variable will have a mean and a standard deviation. We'll have its expected value and a standard deviation. Please refer to the previous page where we have already defined the expected value of the sample mean, which is just the population mean. What is the standard deviation of the sample mean? There are two cases, and it depends on the population. If the population is finite, then the standard deviation of the sample mean will be equal to this rather complicated formula. If the population from which the sample is drawn is infinite, then this is the equation for the standard deviation of the sample mean. Please take a few seconds to understand these equations. Having now established what the expected value and standard deviation of the sample mean are, another nice property is available for us to use. It turns out that when the underlying population has a normal distribution, then the sampling distribution of x bar is also normally distributed. So please, let's refer back to this. Remember the 900 applications? If they're normally distributed, and if we then continuously take 30 samples of 30 and calculate the sample mean, then it turns out that the sample mean will be normally distributed with mean equal to mu, which is the population mean, and a standard deviation equal to the first equation, because the population is finite. So this is a very nice property. If we know that the population is normally distributed, then we can easily work with the sample mean using the normal distribution. But here's another nice thing in the middle box. If the sample size is 30 or more, it doesn't really matter much what the underlying population's distribution is, because we can then still use the normal distribution in working with the sample mean. And in the third box, even if the underlying population is highly skewed, and remember this from chapter 2 where we describe distributions, then so long as the sample size is 50 or greater, then we can then again use the normal distribution. To reiterate, the sampling distribution of the sample mean can be used to provide information about how close the sample mean is to the population mean. And in reference to what we've just discussed, what's called the central limit theorem will be helpful. If the sample size is large enough, then whatever is the distribution of the underlying population, the sampling distribution can be approximated by a normal distribution. What's important, therefore, is to have a large sample size.